So I'm going to talk about topological order. Unfortunately, this is a term that's way overused, and many people will get confused by what I mean by it. So let me just quickly try to say what I mean. I think one simple way to think about it, that these days there's a lot of discussion of topology in condensed matter physics, but you can broadly divide it into two categories. One category you could think of systems that are descendants of the integer quantum Hall effect. So this is an effect that can be understood largely in a free electron picture, but nevertheless there's a topological character to the electron wave function, which leads, for example, to the existence of gapless edge states, which are crucial for the quantization of the Hall effect. And this particular effect is now a huge subject in physics. In particular, there are things called symmetry-protected topological phases, which involve interactions, but really are, in this sense, descendants of the integer quantum Hall effect. The fundamental property being that in the center of the sample, there's nothing exciting going on. You really have to look at the edge to see something exciting. So, however, my talk will be about the second category, but you can think of as descendants of the fractional quantum Hall effect, where there's something unusual and interesting already in the bulk of the sample. Exciting things could happen at the edge, but that will not be my focus. And in fact, most of the states I'll talk about, nothing exciting happens at the edge. But in the bulk, there are excitations in particular, which are topological in the sense that they cannot be created by any local operator on their own. You can create them in composites and separate them, but you could have a region of the sample where there's an excitation which really is protected in the sense there's nothing you can do to remove it or add one more like it on its own.
Question.
Yes?
Does local necessarily, non-local necessarily mean topological? Looks like you're saying once you have a non-local thing, it's topological.
So again, one has to think about examples. I think it does, because if there is some excitation that you can't create on its own, invariably in all the examples I know, you can put it in the hole of a torus. And then the whole wave function of the system depends on the global topology of the system. So I think, I don't know of any counterexamples where, in the sense of, the other sense of the word topological is that somehow the wave function, the many-body ground state, is sensitive to the global topology of the space that it's living on. Anyway, so let me begin by really what's the earliest example of such a state, and that's Wegener's 1971 Ising or Z2 lattice gauge theory. So this is a model on the square lattice, for example, where on each link of the square lattice you have a qubit. So there's a spin and a half degree of freedom that can point up or down on each link of the lattice, and the tau z and tau x are the Pauli matrices that act on that qubit. So this is the particular Hamiltonian that Wegener considered. He didn't use this language, he used a more classical language, but anyway. So there's an interaction which takes the qubits around a plaquette, and you get the product of the tau z operators on this plaquette. And you do this for every plaquette. And so if you use the tau z basis, then the product of the spins around here wants to be +1. Now it can be -1, and I'll refer to that state where the product of tau z is -1 around a plaquette as carrying a flux. So there'll be a flux which has only one value, which is -1. Okay, and that's going to cost some energy because of this negative sign that I put over there. The other term is something that doesn't commute with this term in the Hamiltonian. It's just something that flips the spin with some amplitude g. So this is tau of x. All right, so this Hamiltonian has a very special property, and that might lead you to think that it can't possibly have anything to do with condensed matter, because it has an infinite number of conservation laws. So if you take the product of tau x around a site like this, then this, which I'll call GI, every one of these GIs commutes with the Hamiltonian. It obviously commutes with this, and it commutes with this because, so for example, if I take G on this side, on that side, the parts that don't commute are the tau x here and the tau x there, but each of the tau x is anti-commute with their respective tau z's, and since that gives you 2 minus 1, so it commutes. So every one of these GIs commute, and so if you're going to look at the spectrum of the Hamiltonian, you've got to fix the GI, and we're going to fix it to be 1. All right, so this is what's called the pure Z2 lattice gauge theory. It's a gauge theory because, like any gauge theory, is an infinite number of conserved quantities. And then in that language, this equation, G equals 1, is Gauss's law. It's like del dot E equals 0, which is also an operator that commutes with the Hamiltonian of electrodynamics. Right, so it's hard to imagine that some typical phase of matter could have anything to do with this model, because why should you have all these extra conservation laws? I can easily imagine adding terms here that break this gauge invariance, seemingly, and maybe that's going to destroy the properties. In fact, that's not true, and that's what I'm going to try to explain in different ways. So what Wegener realized was that this is a model which had a phase transition without any local autoparameter, that there was no symmetry breaking autoparameter that was required, but nevertheless there was a phase transition. And he expressed it in terms of the behavior of these non-local objects, which people call Wilson loops, although Wegener came up with it before Wilson, which is just the product of tau z around this contour C. And now in this regime here, it's kind of easy to see that the expectation value of WC will decay exponentially the area of the sample. And you can see that because when G is large, all the spins are pointing in the x direction. And to leading order, then, the expectation value of the Wilson loop operator is just 0. So then you have to do perturbation theory in this plaquette term. And the first term only appears when you go to high enough order in perturbation theory that you tile every plaquette inside this contour, only then you get the first non-zero term. Now this was a model of quark confinement, where you generalize this Z2 gauge to an SU2 group, and then you imagine that you're taking a very heavy quark and moving it around this contour, and the fact that it goes as area law tells you that there's a linear confining potential after appropriate interpretation in the quantum language. But this model, unlike the SU3 gauge theory, also has a deconfined phase where there is no area law, and then this decays as a perimeter. Okay, I won't say more about this because I'm not going to use this description. So this was Wegener's criterion for the existence of a phase transition, but this criterion doesn't really work once you allow the charged particles, like the quarks, to have a finite mass and move on their own. And then you can't use these to distinguish the two phases, although there is a distinction. So the modern way of thinking about Wegener's phase transition is in terms of topology and topological phase transition. So, and this I think is the way I'm going to use prescription here. So in the deconfined phase, let's think about this phase. What happens is that the Z2 flux of -1 that I mentioned is expelled in the ground state, roughly speaking. So what happens when G is small is that you forget this term. And so this product of tau z wants to be 1. So there's no flux. So there's a phase where there's hardly any flux. There's virtual fluctuations of fluxes, but that's it. And then there's another phase where G is very large, where there's lots and lots of flux. So this is sort of analogous to like the Meissner effect. This is like the normal state where magnetic flux penetrates, and this is like the superconducting state where the flux is expelled. But more precisely, what distinguishes these two phases is that here there's a very well-defined excitation. Suppose I do manage to create a flux somehow of flux -1 in a plaquette. That's going to cost me energy. But once I have created that little flux, it'll move around the lattice, and it'll move around and be completely stable. It can't decay. And the reason it can't decay is that there's no operator that can just get rid of the flux. If I take any local operator, it always creates these flux plaquettes in pairs. So if I flip a spin on one line, I create a pair of fluxes on the two plaquettes next to that line. So the number of flux excitation is conserved modulo 2. So if I have an odd number here, it's always going to be an odd number. And so there's a one particle, one low energy excitation that carries Z2 flux. So there's a stable particle here which carries Z2 flux. But on this side, where you're at large G, where flux is fluctuating merrily in the ground state, there's no sense you can quantize the flux, and it proliferates. So that's really the fundamental difference between these two phases. Some of you, I said all of you have heard of Kitaev's famous toric chord, and that's an exactly solvable model which is in this phase. So, and in fact, all the topological properties of the toric chord are already present in this simpler and much earlier Z2 lattice gauge theory. And this theory also has a phase transition. All right, so that's my introduction to topological order and really very simple context. And why, to come back to Pierce's question, why we call it topological, is you imagine taking this system and putting it on a torus, then you can take this flux excitation, this topologically protected excitation in the bulk, and put the flux in the whole of the torus. That'll not going to cost you any energy, but you're going to get a state that's orthogonal to the ground state. So turns out on a torus there's a fourfold degeneracy in the ground state. And on this side, there is no degeneracy. The ground state is unique. So that's a very sharp distinction. You just take your system, put it on a torus, big enough, look at the ground state, you get a fourfold degenerate ground state. Here you won't. And furthermore, this fourfold degeneracy is not associated with any broken symmetry. So that's the topological order. Okay, what I want to do is use these ideas not in systems with a gap, like these two phases have energy gaps, but in systems that are metallic and that have lots of excitations. So some of these criterion don't quite work, but the criterion that there is a stable local excitation like this flux, it still works, and it allows you to distinguish various phases. Okay, so let me begin now with more condensed matter-like models, and I'll talk about some toy models which have this topological phase transition. The G2 gauge is all fine and well, but you could say that's just an artificial model of no interest to us. What about a real model? So let's start with the XY model. So the XY model, and I'll be classical for a while. So if I take the XY model just defined here with some angle theta and an autoparameter phi on a cubic lattice in d dimensions. So when I'm in 3 dimensions, this does have a conventional symmetry breaking phase transition where you have long range order in this phi. And here you have exponentially decaying correlations with this Einstein-Zernike form. And we know really everything there is to know about this phase transition. It's described by the Wilson-Fisher fixed point and all of that. Okay. It's interesting to go back to Kosteles-Thaler's original paper in D equals 2, which, as the Nobel Committee declared, was a topological phase transition. And really, if you look at the first sentence of the paper, they say a new definition of topological order is proposed. And now, I could, Pierce's question could equally be able to ask here, what was topological for them? For them, the idea of topology was that there were these vortex-like excitations. And there were 2 phases, neither with any broken symmetry. But in one phase, there were lots of these vortices. The vortices proliferated. And in the other one, they were expelled. And this is the phase with topological order. So if you take that point of view, their definition is pretty much the same as the definition I'm using, and also distinguishes the 2 phases of the Ising lattice gauge theory. But there is one difference here. In this case, you don't really have to look at topology to distinguish the 2 phases. You could just look at the correlation functions. And in the topological phase, the correlator decays with the power law, and the other decays exponentially. So, so then saying that people, so this is not as shocking. It's not as if there's no symmetry breaking, but there's almost symmetry breaking. So that's why people call this quasi-long range order. the Ising lattice gauge theory has no quasi-long range order. It's short range order or SRO on both sides. All right, so the question I want to ask this is 2 dimensions. What about in 3 dimensions? Is there a way to have a topological phase transition in this very familiar XY model? And this would mean that there's some other phase which has short range order, but is somehow distinct from this one. Okay, so the answer is yes, and I'll show you sketch a model that does that. And so what do you have to do? So let's say we start out with the XY model. Now we want something fancy to happen, so let's imagine we had some higher order terms. So we want to, in particular, add terms which looks at the angles around a plaquette with some KIJKL. And so the broader question is, can this model have some phase transition that is not just the old symmetry breaking phase transition? Can there be more than one type of disordered phase, for example? So the answer is yes. And the way it worked, this is one of the ways to make it work. There are other ways too, but they're more complicated. Is somehow, so this model here has vortices. In fact, they're vortex lines because I'm in 3 dimensions. So what I want to do is to choose these terms that suppresses or likes to expel the elementary vortices, but not the double vortices. I'm going to have to allow vortices, because if I don't have vortices, it turns out you can't get an SRO phase. You'll just have a broken symmetry. So you've got to have vortices, but I only want the double vortices. So can I choose some KIJKL but do this locally? So there's 2 questions. Can I do this? And the second question is this a stable thing? That, maybe locally you suppress double vortices, but eventually when you normalize to long distances, the single vortices come in, and it's actually not anything different. That second question is actually much more subtle. And to answer that second question, the efficient way to do this is to rewrite this term using a clever trick. So what I do here is I introduce an auxiliary variable, sigma ij, which lives on the links of the lattice, and I couple it to this term here, and put a product around every plaquette of the sigma ij. Okay, so this is of course very suggestive, just looks like a Z2 gauge theory, and right, okay, I guess I don't have a slide which explains it a bit more. So let me just say in words, or maybe I use the board. So this particular Hamiltonian, as written down, is basically this model. And the way you can check this is you can just expand in powers of k, and just sum over the sigma ij by hand in the limit of, let's see, small or large k, I forget, small k, I think. And then when you do that, you basically generate these terms. So sigma is just kind of an auxiliary variable. Another crucial property of this action is that it has a gauge invariance, which is the following, that if I take every sigma ij and goes to eta I, sigma ij,
Let him write it first, and then we'll make it.
eta j. So if you make this change of the sigma ij, and also you make a change where e to the I theta I over 2, sorry, I don't remember this exactly. Anyway, it goes to eta I times e to the I theta I over 2. That must mean theta I goes to theta I plus pi eta I, right? Yeah, okay. So if you make these change of variables, where eta I is plus or minus 1, then nothing changes in the Hamiltonian. You can easily check that. On the other hand, if I look at, no, have I got this right? No, I don't have that right, do I? Theta, no, that should be
2 pi.
2 pi. Yes, right. Right, so there's a 2 pi there, and then that cancels this pi and makes sure that this thing is invariant. So you notice from here that however phi I close to phi I. It doesn't change, so it's a gauge invariant. The physical autoparameter is gauge invariant. And that means this theory, even though it doesn't look it, is completely invariant under shifting all the theta I by any constant. And periodic in theta goes to theta plus 2 pi. So it's obviously invariant under shifting theta I and theta j by the same number. But if I change theta I to theta I plus 2 pi, this seems to change, but I can do a gauge transformation and get rid of that. So in fact, this is really, all of this is just to convince you, this is just a rewriting of this model. There's nothing, the sigma ij, this gauge invariance that I've cooked up, is purely an artifact of my choice of variables. Anything observable has all the right properties, it's periodic, and theta goes to theta plus 2 pi, and it only depends on the differences of the angles. Okay.
Sorry, this j on the second line is the square root of that j, or is it exactly?
It's, yeah, it's related to some other way.
relation.
Right, yeah. I think it is something like a square root. Yeah. Okay, now why do I want to do this? Well, because now this coupling K is a very nice coupling to have, because it's exactly what I need to suppress the elementary vortices. So suppose I take this Hamiltonian and build a vortex. So here's a vortex which has 2 pi. And now what happens? So suppose I call this angle close to 0. I go all the way around. This angle here is 2 pi. So now I look at the energy of this bond. Well, that bond, theta I minus theta j is 2 pi. But this is a factor of 2 here. So this becomes minus 1. So this thing is now costing a lot of energy. So I have to compensate for that by making sigma ij minus 1. Okay? So there is, if you wish, a branch cut going out to infinity with every vortex. And along that branch cut, I better flip the sign of sigma ij for the vortex to have, low energy. Otherwise, it's going to cost, this will be a string that costs energy proportional to length. So what this means is that if I look at the flux of sigma ij, the flux of sigma ij is non-zero only here. So it's 0 here, 0 there. But the flux of sigma ij is non-zero only here, and it's minus 1. So what I've done by this parameterization is I've written down an operator, which is this operator, which just measures the presence of vortices. Mod 2, because if I have double vortices, it's back to plus 1. So this is an operator that measures the parity of the local vorticity. And all I want to do now is turn k up, and then I can suppress the odd vortices, but not the even vortices. Okay? So that's the idea. I go back to this model, and then I just turn up my coupling K, and I'm going to get a new phase where I have short-range order and the xy order parameter, as I did here. They decay exponentially. But in this phase, the vortices that I'll see, there'll be lots of vortex loops, but these vortices will be even vortices with winding of 4 pi, 8 pi, and so on, but not the odd vortices. The simple way to say this is that there's a certain Z2 flux variable that's expelled. Whereas in this case, this is the usual Wilson-Fisher disordered phase, has all kinds of vortex loops. So this is starting to look like there's a difference in the topological ordered structure of these. Now there is, to prove it that there's actually a phase transition is a little more subtle, but this is where we have to go back to the Z2 gauge theory picture. So in these two phases, the phi correlations decay exponentially. So I can just, I can do the converse of what I said I should do. Here I was going to explicitly sum over the sigma ij and get an effective theory for the thetas. But there I should do the inverse. I should integrate over the theta i's and get a theory for the sigmas. And that theory for the sigmas will be exactly Wegener's Z2 lattice gauge theory. So we have to go back to Wegener's arguments to prove that there's actually a phase transition here. And in fact, in this case, the universality class is the same, which I haven't discussed, but it's the same as in the pure gauge theory. There's also an interesting difference, but very subtle, in the nature of the order parameter decay. They decay exponentially, but this power law prefactor is different. So in principle, that you could just, if you could do good enough experiment, you could see that difference. And and that has to do with the fractionalization of this order parameter and the fact that the elementary degree of freedom here, when you have only even vortices, is not e to the I theta, it's e to the I theta over 2. And so this order parameter is just the square of an xy order parameter in the long distance.
How do correlations decay just right at the critical point?
I don't know. You'd have to couple, that's a subtle question.
Psi doesn't diverge.
So that theory is a dual Ising theory. So you have to, there's an Ising critical theory, which is coupled to psi via duality Chen-Simons terms. So I don't know, actually. I don't know the answer to that. I'll think about that, but I don't know off the top of my head what the answer is. Yeah, good question. Anyway, so this is then an example of a system which has a topological phase transition in 3 dimension, and hopefully I've convinced you that this can happen in just a simple XY model with some interactions around a plaquette. That's all you need to do. And there have been various numerics and other studies. I don't have the references where this has been seen. In particular, there was a model by Motrnik and Sento where they had a phase diagram, something like this. They were dealing with bosons, but you could do the similar thing for the XY model. All right, so now I want to get to something more relevant. What about the Hubbard model? So if I take the Hubbard model and I do of electron that's some generic filling on the lattice, and I look for a symmetry breaking phase transition. Well, a natural symmetry breaking phase transition is one that leads to antiferromagnetism. So then you have an order parameter, which is the antiferromagnetic order parameter, with the spins having this checkerboard arrangement. And so there can be a phase transition, and this is something you can work out in just basically Hartree-Fock-Mean field theory, from a phase with spin density wave order and a broken spin rotation symmetry, and a phase with no order. Now, however, this is a model with itinerant fermions, so there's something else that goes on across this phase transition. It's not just a broken symmetry. What goes on is that the Fermi surface of the electrons changes. So here, when the order parameter is 0, then it's just a free electron Fermi surface. On the other hand, here, roughly, you can think of the electrons, the mobile fermions, as scattering off this potential due to the moments of the spin density wave order. And because of their Bragg scattering of this potential, which has a period of 2 lattice spacings, the Fermi surface reconstructs, and you get these pockets which are small and large, hole and electron pockets, and so on. So there's 2 things happening at this phase transition. Not only are you, when you go this way, not only are you restoring the symmetry, you're also changing the Fermi surface. All right. But one important thing to keep in mind is that the Luttinger theorem, which constrains the volume enclosed by the Fermi surface, is obeyed in both phases. They're both conventional phases in this language. So here, of course, it's obviously obeyed. All these states inside this Fermi surface are occupied, and that's just the total volume determined by the density of electrons. In this case, it's also obeyed. You just have to keep in mind that the unit cell is now doubled. So your Brillouin zone is halved. You have a small Brillouin zone. And the Luttinger theorem says that the volume enclosed by the Fermi surface is equal to the number of electrons modulo 2 electrons per unit cell. That 2 comes because you can always put a filled band. You're not counting every electron. You're only counting the partially filled bands. So what constitutes a filled band becomes different when you have a doubled unit cell because your Brillouin zone is smaller. So there's no problem with the Luttinger theorem. It just, when properly applied, it holds in both phases. All right, so now what I want to do, I imagine I do the same thing. I have a spin density wave order parameter. And let's say I can go in and add some terms to the Hamiltonian, which prohibits certain vortices in the spin density wave order parameter. Some non-local term, let's imagine. I won't say what it is, but imagine you could do that. And then the question is, can you get another phase up here? And the answer is yes. Now here the topology is a bit more complicated than the XY model because the spin density wave order parameter doesn't live on a circle, it lives on a sphere. But let's, for the purposes of this discussion, for now, imagine it lives on a circle. Well, if it lives on a circle, I have to do exactly what I just told you. I have to suppress the odd vortices. And then I will get a phase in exactly the same way with Z2 topological order. Okay, so this transition from here to there, in that case, would be exactly like in the XY model. All I'm doing is just getting rid of some vortices. And that would be a topological phase transition. But, so there's something much more interesting going on here. Is it turns out that along with this topological phase transition, which was a very subtle thing in the XY model, something dramatic can happen. And what can happen is that the Fermi surface can reconstruct. So you can reconstruct the Fermi surface without actually breaking a symmetry, and then you have violated the Luttinger theorem. So that transition, I guess I've already said that. So here's the same transition shown again. So on this side, where there you had no topological order and spin density wave short-range order, you get the usual Luttinger Fermi surface. But in this side, where you expel the vortices, I'm going to show you now why in such a phase where you expel the vortices, it's possible for you to get Fermi surfaces that do not obey the Luttinger theorem. They look like, these Fermi surfaces look like there's long-range spin density wave order, but there isn't. So there's no broken symmetry. And if there's no broken symmetry in the unit cell, the Brillouin zone is still the full Brillouin zone, then this kind of Fermi surface is not a Luttinger volume. It violates the Luttinger. I won't say violates the Luttinger theorem because the theorem cannot be violated by definition. Some of the conditions of the theorem are not satisfied. Okay. But there is a further theorem, which, okay, it's not really a theorem again, but an argument which is fairly robust, that anytime you have a non-Luttinger volume in any state of matter, then that state of matter must have topological order. Okay, now I won't go through that argument, which is a variant of an argument that was given by Oshikawa to prove the regular Luttinger theorem. But I'll give you just a constructive demonstration of how this works. I'll actually reconstruct the Fermi surface by hand. And all I'm going to need is that I get rid of certain vortices. Okay. And in this case, it turns out the simple way to do that is using actually an SU2 gauge field. So let me go through that argument now. Okay, how am I doing on time?
You're fine.
I have plenty to go to. I just want to time the rest of it.
At least 25 minutes more.
Oh, yeah, okay.
Say 25.
All right, so let me go back to this Hubbard model and try to deal with it somewhat differently. So you can take the Hubbard interaction and you can rewrite it in terms of a spin density wave order parameter, is phi L of I times eta I, that's the spin density wave, I guess. Yeah, phi L is the spin density wave order parameter with some term like phi squared here. And then if you do the integral over phi squared, you get back the Hubbard term. Okay. So now this is just the Hubbard model, and if I'm in a phase where the symmetry is broken, then this Fermi surface of the free electrons will reconstruct. So this is just restating what I just said earlier. So that's the familiar way of getting a phase transition in the Hubbard model. But now let me try to do something else. Imagine that what's happening when spin density wave fluctuations start to gather steam, that the spin density wave order parameter is locally quite large, but it's only fluctuating slowly in its orientation. Okay. So how can I deal with that? Well, one way to deal with that is just by going to a rotating reference frame. So here's my original electron, and on each site I pick a rotating reference frame Ri. This is some SU2 rotation, and these fermions, which I'll call charge-ons, are a new set of fermions, which are the fermions, which are the electrons in the rotating reference frame. All right. Now, when I do this transformation, I should also rotate the spin density wave order parameter. So imagine this locally, well-defined spin density wave order parameter. So I'm going to rotate it, and this rotated order parameter I'm going to call H, and H for Higgs field. This will turn out to be a Higgs field. So the Higgs field is, let's just keep this in mind, this is all you need to know. The Higgs field is the spin density of order in the rotating reference frame.
Excuse me.
Yes.
So near the quantum critical point, if I write the Landau-Ginzburg action for phi,
Yeah. Yeah.
it is actually small.
Yeah, but okay, which quantum critical point? So let me, if I go back, I'll come back to that. I don't want to show my phase diagram. You're talking about the symmetry breaking quantum critical point.
Yes.
I'm far away from there. I'm not going to be anywhere near that quantum critical point. I will have a phase transition, but it's a different phase transition. It'll be a topological phase transition. Okay. Now, why did I call this a Higgs field? Well, because this is actually, the moment I do this, when I go to a rotating reference frame, whether I like it or not, I'm talking about an SU2 gauge theory. Because I can do this rotation. This is ambiguous. I can always insert in here a V dagger V, where V is any SU2 matrix. So I can redefine my charge ons by this factor V. I can redefine my reference frame. And that leaves the physical electrons and the spin density of order invariant, but it changes my H. So H transforms under this gauge transformation. So what's happening here is that this rotating reference frame has a dual role. Its left multiplication is like the physical spin. Its right multiplication is like a gauge transformation. But the Higgs field doesn't carry spin. It only carries gauge. It's like a spin 1 gauge field. It's like a Higgs boson. Okay. All right, so suppose you give me some set of spin density phi that's fluctuating in orientation, and I'm going to come in and straighten it out. I'm going to rotate so that even though phi is fluctuating, H is not. Suppose I can do that. So I go into a rotating reference frame everywhere. And then I rotate every phi into the z direction, let's say. I just keep doing that everywhere. And then I will get a Hamiltonian for my charge ons. In the rotating reference frame, I have these new fermions whose frame of reference is rotating. Now that rotation of the reference frame will renormalize this hopping a bit, but I'm going to ignore that. But most importantly, in the rotating reference frame, the local antiferromagnetic order will be just the Higgs field. And now I'm going to make this a constant. Suppose I can make this a constant. Well, if I do that, then
Question.
I see, yes.
Why isn't there a gauge term on the hopping of the
There is. I've just simplified that for now. I'm just looking at some effect. I'm assuming, suppose I can do this transformation and ignore all the fluctuations and the gauge terms, yes. The quick answer is that when you're in the Higgs phase, the gauge fluctuations are suppressed, at least in the Z2 case.
But there is still an overall mean field normalization.
Yes, there's a renormalization, correct. Yes. All right, so if I can do this, and this is constant, then these psi fermions see a constant H, and so their Fermi surface will reconstruct. As far as the psi rotated fermions are concerned, there's long-range order. I've just rotated it out. I just straightened it out everywhere. There's long-range order. And these psi fermions will have a small Fermi surface, if they're really free to move around. So at this point, it's useful to recall, what is Luttinger's theorem? The more general statement of Luttinger's theorem, there's a Luttinger theorem statement for any global U1 symmetry. In this case, it's just conservation of charge. And the total volume of all fermions that carry the global charge must equal the total charge density. So in this case, the psi fermions do carry electromagnetic charge. They're charged, that's why I call them charge ons. So the Luttinger theorem applies to the charge ons. So they have small Fermi surfaces, and then since I haven't broken any symmetry, I've just gone into a rotating reference frame. I have violated the Luttinger theorem. Okay. This can't possibly be correct, because if I could always do this, there is no theorem. So why can't I do this? Well, of course, no surprise. The reason you can't do this are the defects. So suppose you give me, let's now imagine, against simplicity, that the spins all lie in a plane. So, and I told you they're just fluctuating in orientation. Well, they're fluctuating in orientation, but locally large. But just so happens that there's this vortex-like configuration sitting here. Now I want to rotate the spin so that they all point in the same direction. So I pick an R, but as I go around, remember this is an SU2 rotation. So if I do an SU2 rotation by 2 pi, it gives you a -1. So I'm not allowed, I can't do it because of this obstruction. So this particular configuration cannot be just caged away. It's going to have a pi flux here, which is going to cost some energy if you really had this state. So really, to be able to freely rotate back to a constant Higgs field, I better have a configuration in which the original STW autoparameter doesn't have vortices. But you can see I can have double vortices, no problem. R will come back to R. So that's the sneaky reason I talked about double vortices. So therefore, this Higgs phase where H is locally constant, but the orientation of the autoparameter is fluctuating, is a phase in which such vortices cost energy. They carry pi flux for the easy plane case, and they must be expelled in the ground state, and they are excited states above the ground state. They're topological excitations, which are stable. So therefore, by the language I'm using, yes, such a phase can exist. Now, yes, I can get small Fermi surfaces, but that better be a state that has these vortices expelled. So it has to have topological order. So that's my simple illustration of why there's this intimate connection between the size of the Fermi surface and topological order. Roughly speaking, another way to say this is that when you have topological order, you have a certain gauge degree of freedom in defining your fermions. And you can use that gauge degree of freedom to actually change the size of a unit cell. You could have long-range antiferromagnetic order in a rotating reference frame. All gauge-invariant quantities don't break the symmetry, but the gauge-dependent quantities do, and that's enough to actually get a smaller Fermi surface.
Question?
Yeah.
Is this a vortex or a skyrmia?
So that's why I said I'm considering easy plane. Suppose there's a spin orbit term that makes it easy.
Okay. All right.
If you want to talk about Heisenberg spins, so then the defects you have to suppress are actually hedgehogs.
Yes. Okay.
Which are events which are more subtle. They're tunneling events where the skyrmion number changes.
Okay. So in space, you mean in space-time? Yeah.
Yes. So what that would mean if you want to violate the Luttinger theorem with SU2 spins, full spins in a sphere, then your phase will be a phase which has an emergent conservation law, that the total number of skyrmions is conserved. So if you suppress skyrmion number changing events, then that's a topological phase that can have a different volume of the Fermi surface. All right, so that's this phase diagram again. Did I show this before? No, I did show this. Okay. So I can also address Yashar's question. So in terms of the old order parameter, phi, the phi was 0 here and 0 there and non-zero here. This is the conventional phase. This is the conventional Fermi liquid. This is the new phase. But in terms of the new Higgs field, the Higgs field is non-zero here. That's the topological phase. And here the Higgs field is 0. So, right. So here the Higgs field is fluctuating a lot, and here it just freezes. And when it freezes, you can go into a rotating reference frame and get a small Fermi surface. And also, the freezing of the Higgs field means that these vortices in the Higgs field cost a lot of energy, and that's the topological order.
So my question is that this theory should also be valid near the left boundary, where the phi is negligible.
Here?
Yes, the value of the phi should be negligible, right?
Okay, so this boundary is a little more subtle. Well, no, it's actually simpler. So the way you think about this, phi is roughly like the product of H and R. So in this phase, really, everything is broken. You can say that there's no fluctuation in the rotating reference frame, and there's no fluctuation in the Higgs field. And here the Higgs field is also constant. So what you're condensing here is just the R. So this is the transition where the frame of reference condenses. And that's a topological transition because this R, again, it's a SU2 object, not an SO3 object. So the order parameter is not of O3 vector, it's an SU2 matrix. So that extra Z2 means that there's something topological about it. All right. Okay, so that's the theoretical story I wanted to present, how you can get, there's many different ways of thinking about it, but you can think in terms of suppressing certain defects. You can think in terms of some gauge theory where you're going from in this case, a confining phase to a Higgs phase. And in this Higgs phase, the certain topological defects become, which are analogs of Abrikosov vortices, become allowed. And also you can reconstruct the Fermi surface. What the nature of this phase transition is still a pretty much open question. And the other two, I think, are pretty much cleaner to analyze. All right, so now let me try to argue that this particular phase has many features that make it very suggestive that it's also been realized in a lot of numerical studies of the Hubbard model. So this is my quick summary of things that I'm not an expert at. Many people have studied by a variety of methods the phase diagram of the Hubbard model at low hole doping. And everyone agrees that there seems to be some phase that's highly unusual. It's not a Fermi liquid. It doesn't seem to have any broken symmetry. And many bizarre things seem to be going on. And this is just a partial list of references, and I'm sure many of you know much more about this than I do. But anyway, I've been following this literature for a while over the years and trying to really figure out what's going on. And in the recent work with Antoine, we're, I think, starting to see that there is actually some synergy or convergence here. So what have these cluster DMFT studies shown? So one of the things they show is sometimes called momentum space differentiation, which means that if you look at the electron self-energy in the antinodal region, which is near the momentum pi 0 in the Brillouin zone, there seems to be like a pole almost developing, which is interpreted as saying that somehow the antinodal region looks like a Mott insulator. Whereas in the nodal region, around this direction, there is no such pole. So this is one general feature in a lot of studies. Associated with that is if you look at so what's shown here are, I think, this particular plot in the paper was Stanescu and Kotliar. I think these are actual numerical studies, and these are some interpolations. Their guess as to what the Green's function actually is at 0 temperature. So there's gapped spectrum in the antinodes, meaning that let's see, what the hell, this is the A of k and omega, so there is no intensity there at all. And then there's a lot of intensity in the nodal region, and this is the arc-like structure. And another feature that's found in many of these studies is that the Green's function itself, which is, has a zero, apparent zero, or near zero. And this is very clearly connected to the pole and the self-energy. The self-energy is infinite, the Green's function is 0. So here's a sketch in this paper that's the line of zeros of the Green's function. And this is the Fermi surface that they're apparently getting. And because of the proximity of the line of zeros, the intensity on the B part of the Fermi surface is very small or negligible. It's basically not seen. All right, and there have been also many arguments that this line of zeros is how you can reconcile the violation of the Latente theorem in such states. Okay, so
the left panel is higher doping where things more conventional.
No.
Yes,
I think the left panel is just R of k, and the right panel is A of k and omega.
No, the left panel is much higher doping.
Oh, thank you. Right, n equals 0.78 and 0.9.
And where everything is conventional, and the right panel.
Thank you. Right.
Is lower doping where exotic things happen.
All right. So this is all very suggestive and very much the inspiration of our work. I don't quite agree with some of these statements. In particular, what I want to show you is that there's no real zero of the Green's function, and it directly doesn't have anything to do with the Blood-Inter theorem. What there is an approximate zero.
But there is still a sign change of the
Yeah.
real part.
Yes, okay. There is an approximate zero, and what it's really telling you that it's really a harbinger or a signal of topological order. And the correct way to understand the absence of Blood-Inter theorem is the topological order. So let me show you how this works. So I'll just take the same theory I just described. So suppose I'm in this Higgs phase, this new phase at the top. So as I said earlier, there I can just imagine the charge-ons are moving freely in the presence of a constant antiferromagnetic background. Okay? So now let me compute the Green's function of these charge-ons. Those are not the electrons, mind you. Okay? So if I just compute the Green's function of these charge-ons in this simple approximation, this is what you get. This is the diagonal Green's function, GKK. There's also an off-diagonal piece, but let me not write that up. So if I ignore the off-diagonal piece and just take the diagonal Green's function, the self-energy is the Higgs field squared minus omega minus EK plus Q. So now if I look at this Green's function, it has all of these properties that I just discussed. One is that at omega equals 0, there's a pole in the self-energy when EK plus Q equals 0. So that is not very far from, well, it's something like that line, dashed line over there. Well, actually, in this case, it'll curve a little differently, but anyway, there's some line over there where the Green's function vanishes, and there's a similar line here. I'll show you the line in our calculation.
Question?
Yes,
What would happen at absolute zero?
I'm talking about absolute zero.
So how could you avoid having zeros at these singular points without having imaginary parts to the self-energy?
I agree, there's no such thing as zeros. Yeah, this is just an approximation, but
But that would require phase space for scattering.
sorry. So what I thought you were saying, so there is a statement, poles so Green's function is complex.
Right.
So to get a zero of the Green's function, you have to satisfy two equations. Now it's also true to get a pole in the Green's function, you have to satisfy two equations. Both the inverse, real and imaginary part of G inverse have to vanish. Now it just so turns out that the structure of perturbation theory is such that if the real part of the inverse of the Green's function vanishes, the imaginary part can also vanish generically. So you only have to demand that the real part of the inverse of the Green's function vanish as one condition. Yeah, real part of the inverse, not the other way around. There's only one condition to find a Fermi surface of poles. But there's no such condition on the zeros of the Green's function. The Green function generically a complex number in a gapless phase. So you have to satisfy two equations. So strict zeros are not lines, they are points. They don't even exist. Okay. Now in this simple approximation, they exist because I've just ignored the damping.
But wait, I'm sorry, can I attempt
Yeah.
to restate my distinguished colleague's
Okay.
question?
Right.
So you're free.
So I think we would agree, just based on what we know from many approximations, that if I consider only the real part of the Green's function at zero frequency,
Yeah.
then there is a sign change as I move around
Okay,
in
fine.
K-space. So there
Yeah.
has to be a line somewheres where the real part
Right.
vanishes.
But that doesn't help you as far as
I understand, but
yeah.
one step at a time. Okay.
Yes, I
So
agree.
then, the next statement, which I think where Piers is coming from, is that if I consider really omega equals 0, then there should be no phase space for scattering, and therefore the imaginary part should also just generically be 0.
That was my kind
That
of-
was,
I think
that
that's what
was
he
where
said.
he was coming
Yeah,
from.
yeah.
So the question is, if I sit at omega equals 0, so I'm
Yeah.
considering the locus of 0 energy excitations, how can I have an imaginary part of anything?
Right,
That was his
Thank
question.
you for phrasing it clearly.
I don't think there's any problem in a Fermi liquid, I guess.
Well, in Fermi liquid, there is no imaginary
No,
part at
but-
0 frequency at 0 temperature. That's the...
No, but I think the answer to this question is that if you had a sharp pole,
Yes.
sigma,
Yes,
the imaginary part
yes.
is a delta function, obviously. The
Okay.
imaginary part of that guy is a delta
Okay.
function.
All right.
So that phase space argument doesn't work, because you have to accept the fact that the imaginary part of sigma is not 0, but actually has a delta
So this
function.
is not a Fermi liquid then, it's a
Well,
non
it's,
Fermi liquid.
it's as far as a Fermi liquid from anything you can think of.
Okay.
Well, let's see. So, but you're saying in a Fermi liquid, if there happen to be a zero, the Green's function
I
at
think
zero.
what they are saying, one of the statements is that what you said that by some magical reason, the two conditions dissolve into just one.
Yes, well, they certainly do for the poles.
Pierce's argument that there is no phase space, and as you go to omega
Yeah.
equals 0 on the Fermi surface, the imaginary part is 0.
No, if you go to
anyhow.
omega equals 0 anywhere, not just on the Fermi surface, the
Yes.
imaginary part is 0.
Yeah,
because
exactly.
There's no phase space.
Right.
That's the point.
Yeah, that's the point.
That's the magic that happens in Fermi liquid theory, at least as we learned taught it.
I think this is not a Fermi liquid, so you're okay, probably.
Well, but
No,
there's
no.
still the physics question of imaginary particle self-energy is associated with scattering. And
No, I mean,
if
come on,
zero, there's
but-
no phase space for scattering. That's the point.
But aren't there multi-particle excitations, but you're saying their density of states vanishes
Yeah,
at
there's no
zero?
phase space for it. So at omega goes to 0, you
Yes.
just think of,
Yes,
sharing energy, there's no phase space. So there's something devious, as Antoine said, about having a whole structure in the self-energy.
well, if you put in a little bit of disorder, there's certainly a finite
Well,
density.
once you have disorder, then life gets
Yes.
different. But let's just talk about clean.
I mean, we take the case of a Kondo lattice, where you form
Yeah.
a large Fermi surface. There, in the electron Green's function, there are indeed those zeros of the Green's function.
With the same structure, with
With
the
the
delta
with the
function
very strange
form of
structures.
the
My
imaginary
related
part.
question was, should I think of a large Fermi surface Kondo lattice as a state of topological order?
Well, it depends. A large Fermi surface constant, no,
Yeah,
probably
because there I'll
not.
have the zeros, there I'll have the...
No, he's
The-
saying,
the-
but if I have fermions plus spins, I have only a small number of fermions, so by themselves they have a small Fermi surface.
Yes.
Then the actual Kondo lattice ground state has a big Fermi surface.
Yes.
Because we've dissolved the spins into it, so is that?
Yeah, that certainly does not have topological order.
No, the phase which would have topological order is the phase in
It's a
which
small
there is the small Fermi surface in the Kondo lattice. There
Right.
you need the topological.
Absolutely, yes. Correct.
But there
That's the opposite.
I've got zeros, it's the opposite of this case. There I've got zeros in the conduction electron Green's function.
Here, actually, may I suggest, I personally find this discussion completely fascinating, but I propose that we continue it. I propose that we continue it offline in front of a blackboard. As
All right.
the engineer finishes talking.
Yes.
Yes, I have to think this through, but
British understatement.
I know this, but I don't feel that we should make everybody wait to educate me.
all right, but, yeah, okay. Where was I? All right. So what we're going to do is take this very simple approximation and convolute it with these spin-ons, because, so basically, we're going to reconstitute the electrons, and we assume some small gap for these R excitations, and we compute the electron spectral function. So in this simple approximation, there is a zero of the charge-on spectral function. That's the zero over there, and these are the pockets in the charge-on spectral function. When you do this convolution, and these things move around a bit. There's now a zero in the real part of the Green's function. That's the red line, and this is the spectral density of the physical electrons. Okay. So now in this phase, how is the Luttinger theorem satisfied? How does it all work? The claim has absolutely nothing to do with any of this zero structure. It has to do with the presence of long-range order in the rotating reference frame. So the way you think about the Luttinger theorem now is you just happen to notice that since it's just a rotating reference frame, the density of electrons is the density of the charge-ons. So why don't I just go ahead and compute the density of charge-ons? Because it's the same as that. Okay, so let me go to the Higgs phase, where you have these charge-ons. Now, as far as the charge-ons are concerned in the Higgs phase, there is long-range antiferromagnetic order. Now, that doesn't mean translational symmetry is broken, because none of this is gauge invariant. The charge-ons themselves and the Higgs fields themselves are not gauge invariant objects. So it's very much like, when you have a magnetic field, you're not breaking any translational symmetry, but you have to pick a gauge, and you pick a gauge, you double or triple or something the unit cell. You're playing the same trick here, except that here the gauge field is emergent. So if I apply the Luttinger argument to the charge-ons, then everything works. I can apply the usual Luttinger argument, just provided I apply it in this phase, in this gauge, where I have picked long-range order for the charge-ons. So it's really as simple as that. Yeah, I guess I've already said this. And I think I already said that too. The topological order allows one to break translational symmetry in gauge-dependent quantities, but preserve it in all gauge-invariant observables. And that's enough to get a state, a potentially stable down to zero temperature, in which there's a non-Luttinger volume. Okay, and these are some more detailed comparisons between this simple SU2 gauge here. I just described the calculation. It's very simple. You assume long-range order for the charge-ons, and you can convolute the result with the spin-on. So in this case, there is a fitting parameter, and the fitting parameter is this size of the pseudogap at the antinodes, which is the magnitude of the Higgs field. That has nothing directly to do with the spin correlation length, which is determined more by the spin-on gap. And so this is a comparison between DCA results and Higgs theory, where I think this is fitted this to that. And this is in the same calculation, the imaginary part and the real part of the self-energy at the dashed and dotted lines correspond to two different values of T prime, I think. And you can see the structure is almost exactly the same. So this increase here is the pole in the self-energy. It's not a true pole, it gets rounded out. And in our case, in the calculation, this is getting rounding out simply by this convolution. So there is a pole here, but when we go to just do this convolution, that just gets rounded out. Okay. All right, so this is, I really should ask Antoine more about this. This is looking at various trends in the shape of the Fermi surface as you change the value of T prime and doping. Now, if you just take the bare electron dispersion and try to compute these trends and when it goes from a Fermi surface like this to like this, you get very different answers from what's actually seen in numerical calculations. But the SU2 gauge theory, after you account for the normalization of the hopping parameter, gets you trends that are closer to the numerical computations. Okay, so that's really all I have to say. I've given you 3 or so. Yeah, I'm out of time. I've discussed some very simple examples, some old examples of topological order and how you can get that in conventional XY models, and then a proposal that similar states are also present in the Hubbard model. And you can understand these topological states more generally, and rather than you don't have to put on a torus, you don't have to have a gap. It's really, I think, a powerful way of thinking about these phases is suppressing certain subsets of the defects in the state where you have some fluctuating order. So you have some order parameter, you allow it to fluctuate, but not completely. You just restrict it in some way, and that's enough to give you interesting new phases of matter. Another way of thinking about it is in terms of emergent gauge fields. I mean, you can choose this one if you want, you don't have to do this, but this is often much more convenient for calculations and also for understanding phase transitions. You introduce emergent gauge fields, and then by breaking the emergent gauge symmetry down to different Higgs fields, you can get all kinds of phases. And in this case, the defects that are being suppressed here are the vortices of the Higgs phase, like the Abrikosov vortices of a superconductor. And what was that? Yes. And okay, so this kind of approach seems to be consistent, at least with cluster DMFT. I had a couple of slides on an experiment, which I'll quickly flash through. So why should this? So the hope, ultimately, in my mind, is that this type of phase transition here. Oh, sorry, I'll show that. So, okay, the phase transition here across this way has something to do with many experimental indications of a phase transition near the optimal doping region in the cuprates. So that phase transition may have something to do with this transition. And in particular, if you take this simple SU2 gauge theory and compute the Hall coefficient in a simple model as a function of doping, it's actually very similar to the Hall coefficient in the case of onset of antiferromagnetic order. But here you don't have any order. That can at least fit some of this data that garnered a lot of attention. But all right. But that's very much work in progress. and we are thinking a lot more about the nature of this critical point. Thank you.
Thank you very much, Subir. Take us from Z2 gauge field to Q-praise. That was very great. So questions?
Two questions. One is that do you expect, putting on the torus, do you expect some ground-set degeneracy on the topological phase?
Yes. But, okay, so what's the difference? It's subtle, though. So when you have like a toric core, and you put it on a torus, then you get a four-fold ground-state degeneracy. Well, not strictly. You get four states that are separated exponential in the system size. E to the minus L is the space between the states. So here, what's going to happen? Now, suppose I take a Fermi liquid and I put it on a torus. Then what will happen is I'll get a whole bunch of levels. Their spacing is 1 over L. Okay? And in principle, if you studied those levels very carefully, you could figure out, what the dispersion of your quasi-particles. You can know something about your quasi-particles. So what's going to happen in the topological phase, that is this phase as opposed to even this phase, that is that if you look at the energy levels, first of all, they'll all be spaced by 1 over L, but they cannot be understood simply by quasi-particles. There'll be actually, there'll roughly speaking be 4 copies of every level, which will also be spaced by 1 over L, unfortunately. So it's not so easy to just entangle. But there will be states where you put flux pi through the whole of the torus, for example, and that will differ in energy, even the ground state, from the other state by energy of about 1 over L, unfortunately, not exponentially, because they are gauge charged particles. As long as there's a charge on Fermi surface, that will make that energy difference a bit larger. Anyway, so the short answer is it's not just a matter of looking at degeneracy. You have to look at the entire tower of states on a torus. And if you work hard enough, that tower of states will tell you that there is topological order.
So another question is that, do you expect similar physics near other symmetry breaking phase transitions?
Yes.
Like a charge density or superconductivity, for example?
In principle, you can take any, so there is a version of this theory where you could do this for superconductivity. Many people have worked on it. In one way you can think of the theory of the pseudo gap by Nagosa, Lee, and Wen. They assume effectively that there's an approximate SU2 pseudo-spin symmetry, of which superconductivity is one. They generalize it to SU2, and then you go to a rotating reference frame of the pseudo-spin SU2. So their theory is very much can be restated in this language as just Higgs phases of a rotating reference frame in the pseudo-spin space. Yeah, I mean, almost any gauge, I think that's a very general way of thinking of any gauge theory. You take, at least my point of view, you take some exact or approximate, it doesn't have to be exact. You take an exact or approximate symmetry, and then you gauge it by going to a rotating reference frame, and then you can get this type of phase diagram.
Okay.
Okay, I'd like to ask you about the temperature dependence of the...
Can you
The
speak
what?
a bit louder?
The temperature dependence of the self-energy.
Yes.
If we do the cross BMFT, for example, if we go to the lower temperature, then
Yeah.
the self-energy of the peak of the self-energy grows
Yes.
Yes.
sharper and sharper.
Right.
In
So
theory, so you showed some comparison, right?
yes. So
Is it finite temperature result or?
these are finite temperature results. Yeah. So I mean, what you're asking for would require some kind of complete theory of the strength of this Higgs field. Unfortunately, we don't have that. I mean, we just get that from the DMFT. You can do a theory. If you try to do a theory, it'll be nothing but the usual spin density wave theory, which we know is not very accurate at all.
No, but just to complement this, I mean,
Yeah.
all this is also done by assuming that there is a small spin-on gap and the temperature is larger than that.
Yes, of course.
So to fully answer use case question, one would also have to have a description of the temperature dependence of the spin-on gap in the gauge theory, which eventually may close or not, depending on, but, right?
Yeah. sure.
Because nominally, in the
Yes.
simplest mean field that you have described, here,
Right, right, yeah.
the zero temperature ground state is gapped everywhere. At zero temperature. The physical electron.
Yeah, but there's not gapped. I mean, there is a Fermi surface of
because
charge
there's a
on
spin-on gap.
in the photo emission spectrum.
Hmm?
In the
Yeah,
photo emission
physical
spectrum.
fermion
That's what I'm
spectrum.
saying, the physical electron. But
Yes.
that's what this guy is talking about. He's talking about the physical electron self-energy.
Yes. Well,
So if we take literally the SU2 mean field that is being done there with
Yeah.
a fixed spin-on gap,
yes,
at zero temperature, there's just no physical electron Fermi surface.
that's correct. Yes.
And this somehow is a little bit of a problem for matching
Well, okay.
what's
So
going on at low T in the numerics. and
right.
SU2
Well,
mean.
so, but one way to get out of this is you imagine there's a bound state that forms between the spin-on and the charge-ons, and
That's
you get this FL star state, and I've done various calculations where we see that actually happens, but yes, that's a more subtle thing. Yeah.
But can I just ask,
Yeah.
sort of along the same lines,
Yeah.
I guess it's implicit, but you didn't really say it. Within this theory of the phase with the broken gauge symmetry, but not
Yes.
the Higgs phase.
Yes.
Right. How do I think about the temperature dependence? Basically, does the R field get exponential correlations, or? Yeah,
Yes.
I mean, in here, how do you want me to think about the temperature dependence?
In here, up here.
Yeah.
Yeah. Well, the R field is a gap, and
Right,
so
that
it's,
does not, yeah.
so if the temperature is bigger than the gap, then the correlation length will be proportional, inverse correlation length proportional to temperature roughly. And when the temperature is smaller than the gap, it will be actually be just constant. It's not, right?
So it basically is a finite value of the correlation length,
Yeah.
which is some function of temperature divided by the gap
Yeah.
of the R field, and that will lead to even more broadening of the
Right. So I mean, so that picture, has some issues with the spin susceptibility across this transition, which it seems like there's a large Pauli susceptibility at this transition, and so if I just take this SU2 gauge theory on its own as a theory of this transition, I run into trouble with the behavior of the spin susceptibility. But there, could be other things going on. I mean, I think this is a picture of what's happening at relatively high temperatures, and as you lower the temperature, in this phase, one simplest thing could happen is that there's a bound state of the R and the psi, and these actually become electron pockets. So that's the phase we call FL star. So that can emerge.
But
very
in fact,
naturally.
this is the only way
Yes.
you can have a physical electron Fermi surface in that theory. Because
Yes,
if you were
correct.
arguing about closing of the spin-on gap,
Yes.
that would also lead to diverging psi. Isn't it?
Closing of spin-on gap happens. You just get long-range order.
Yeah, that's what I'm saying.
Yeah.
Yeah, exactly.
Yeah. Yeah. Well. I mean, these are all issues I've played around in various models over the years, so I can defend myself that way. But I think I would say that this simple theory, does quite surprisingly well over a certain temperature range. And what really happens at low temperature is still an open question.
So and again, along those lines, I'm sorry to be selfish, but just in terms of what
Yeah.
may really happen within the theory at low temperatures, how do I think about adding superconductivity to this?
Well, you can just pair the charge-ons.
Okay, so in this view, the spin gap is the spin-on gap of the superconductor, and superconductivity is just kind of a superfluidity of the charge-ons which get paired. That's how I should think about it in this
Well,
picture.
so there is a subtlety there too.
Uh-huh.
If you just pair the charge-ons of opposite gauge charges, then the pairing itself breaks the external U1 symmetry, but if there was a U1 gauge, if there was a topological order, it's actually not destroyed.
Right.
So what you will get is actually yet another topological superconductor, nothing to do with the topological superconductor that other people are talking
Right.
about. So you do get a rather anomalous states. On the other hand, once the charge-ons pair, then there's nothing preventing the gauge field from undergoing a confinement transition. So the onset of superconductivity could also be associated with the onset of confinement. In
Is
fact-
that a smoking gun experimental signature of the topological superconductor?
It would have 8 nodes.
Ah, I see it, okay, yeah. Great, thank you.
Okay? More questions? questions to Subir?
But of course, the spectral density of the back would be very small. I mean, no one's seen the backside. But in principle, the specific heat should give you 8 nodes.
Okay, so I think we can thank Subir again.